Right, good afternoon, everyone. Okay, so we are going to look at work example 3. Now, before you continue watching, if you have not tried this question, if you have not attempted, please pause this video and attempt now. Give yourself about 5 to 10 minutes. Okay, it'll always be beneficial if you start first, right? If you try to understand it yourself first, and then when I explain the question, you'll be like, oh, okay, these are some parts that I missed out perhaps. Okay, so pause the video if you have not tried this question. Now, if you have tried already, okay, can you please include these two, make sure you have include these two sets of information, right? I forgot to list them out when I set this question, right? In any case, these values can be easily obtained from the internet. Why? It's always a constant value, right, for that particular material. Okay, because it's like an inherent property of that material, like your density. Now, let's look at this question together. During a camping trip, 40 grams of aluminium cup was placed near a campfire heated to 120 degrees Celsius. Alex then poured 250 grams of river water. I should circle the unit also. Water at 20 degrees Celsius into the cup to cool it down. Assume that energy is transferred only from aluminum cup to the water. Calculate final temperature. So the hint says, okay, both the cup and water will reach the same final temperature. Now, when you face a question like this, right, always good to try and visualize how, or rather visualize what this scenario looks like. So imagine I have a hot aluminum cup. In this case, it is at 120 degrees Celsius when it was placed near the campfire. Then afterwards, I pour water on it. I pour water. So I pour water. Okay, and these water are at 20 degrees Celsius. So what's going to happen between these two material? One that's hotter, one that's cooler, right? So when there's a temperature difference, energy transfer is going to take place, right? Or rather, a net energy transfer. So since the energy is only transferred between the cup and water, so we don't need to care about energy going into the surrounding. We can ignore this. In this case, I know that, okay, in terms of visualizing how the energy flows, it will have to flow from aluminum cup all the way into water. Okay, so based on this statement, the energy from aluminum cup uh, energy loss, okay, is going into energy gain in water. So in this case, how can I link this to the specific heat capacity? Because these are the other information I was given, right? Specific capacity and the mass and temperature change. Okay, so this is the formula that will be involved, right? MC delta theta. Right. So what's Q? Q is the energy transfer. Okay, so either you gain energy or you lose energy. So in this case, I'm gonna apply them and I will denote two different subscripts. So I'm going to use A to denote aluminium. So QA is equals to QW. W represents water. So now I apply, right? MACA delta A, which stands for the change in temperature of water, change in temperature of water, sorry, of aluminium. And afterwards, this is equivalent to the mass of water involved, the specific capacity of water, and the corresponding temperature change of water. MC blah blah blah. Now, later we'll have to try and break this up, right? This change in the temperature to include their common temperature, their common final temperature. Okay, both of them have different initial temperature. Okay, but before that, let me uh substitute whatever values I can first. So in this case, since my specific capacity values are based on SI unit, okay, the temperature don't really matter lah because it's change ma. Whether is it change in Kelvin or change in degree Celsius, they both mean the same amount of quantity. So can safely ignore that. Okay. So MA, mass of aluminium is 40 grams. So I need to convert that into SI unit. So 40 grams divided by 1000, that gives me 0.04 kg. Okay, so that's why 0.04 multiplied by the specific heat capacity of aluminium, which is 900, right? Okay, I'll leave it as it is first, the change in temperature. Then for water, 250 grams, that's equivalent to 0.25 kg. So 0.25 times CW, which is 4200, multiplied by change in temperature of water. Okay, so now up to you. Usually I will maybe at this point, since there's no commonality, right? I can try to simplify first the numbers. 0.04 times 900 is 36 equals to 0.25 times 4200. That's 1050 times the change in temperature of water. Now, let's break the change now. So I know that because this is the energy loss by aluminium, right? So will the final temperature be lower than 120 or higher? Okay, it should be lower, right? So in that case, since I just want to know the difference in value, and I will usually to find the just the magnitude of the difference, I will usually take the larger value minus the smaller value. Okay, so in this case, 36, what does it multiply? Right, it will have to be 120 degrees Celsius minus that final temperature. I'm going to denote with theta F. F stands for final. Okay, now feel free to write it out in full. If let's say too many letters, you get very confused. So for water, 1050, how will the change in the temperature for water be like? Whether is the final temperature gonna be larger than 20 or lower? Okay, it has to be larger. So in that case, my final temperature will be the first value, right? Subtracting the smaller value, 20 degrees Celsius, because over here it's gain in energy, right? So therefore, now I just need to make use of my algebraic skill. Okay, I just need to expand them. So 4320, expand it, minus 36, final, 1050, theta final, minus 1050 times 20, 1000. Okay, so then I just have to manipulate the algebra again. 1086 theta final equals to 21000 plus 4320. 25320. So therefore, heater final will just be 23.3149. 23.3 degrees Celsius USF. Okay, so that's how you solve this question. So I'll upload this onto Google Classroom. Okay, thank you everyone.